Great day to all! Today ay magdidiscuss tayo ng dalawa pang circuit configurations ng bipolar junction transistors. Namely, yung common emitter at yung common collector. But before that, a bit of info about sa kung sinong nag-imbento ng transistor. They were scientists from the Bell Telephone Laboratories. Ito ay sina John Bardeen, si William Shockley na yung gumawa ng Shockley's equation for diodes, and in our future discussions, magkakaroon tayo ng Shockley's equation for field effect transistors. And lastly, we have Walter Brattain. In 1947, naipakita nila na ang transistor pala ay pwedeng makapag-amplify ng mga signals. Ang inimbento nila dati ay hindi kagaya ng mga transistors ngayon na nakikita natin sa mga modern circuits natin. Ito yung tinatawag na point contact transistor. So medyo malaki yung kanilang prototype for the transistor kasi wala pa namang manufacturing process to make or manufacture yung mga small scale na mga transistors natin na ginagamit natin sa mga modern circuits natin. This is the point contact transistor. Ito yung dinevelop ng tatlong scientists na yon noong 1940s. We have the different parts, the plastic frame, the spring, the plastic wedge. Pero ito yung pinaka-importante, yung ating semiconductor material, which is at that time, pinag-eksperimentohan nila yung germanium. You have the P-type and you have the N-type material. You have the metal base. At of course, kagaya ng ating mga transistors na ginagamit ngayon, ng BJTs na ginagamit natin in the modern world, meron din siyang tatlong terminals. We have the emitter, the base, and we have the collector. Noong 1951 naman, si William Shockley ay nakaimbento nung kauna-unahang junction transistor. So meron tayong P-type at N-type material na pinagdugtong, no? At it will form your BJT. So we have PNP and we have the NPN. Etong dinevelop ni Shockley na ito, it paved the way for advanced and for modern electronics na umunlad, no? And isa sa pinakamahalagang development na nangyari dahil dito sa ginawa ni Shockley ay yung nagkaroon tayo ng tinatawag ng mga ICs or integrated circuits. No, alam naman natin yung mga ICs natin, merong mga transistors na nasa loob niya. So it depends kung ilan yung laman na transistor nasa loob, no? So we have LSI, VLSI, so on and so forth. So anyway, we will discuss that in our future lectures. And now we proceed to the common emitter configuration. Ito yung pangalawang configuration ng ating BJT. Kung mapapansin natin dito sa ating diagram, we have an NPN BJT. We have the emitter, the base, and the collector terminals or layers. Ang ating emitter ay direktang nakakonekta sa ground. Okay? Ang common emitter, ang input terminal niya ay base. Ang output terminal naman niya ay ang ating collector. Okay? So, ibig sabihin, ang input side natin ay base emitter, ang output side ay collector emitter. So, common yung emitter both to the input side and to the output side. But, this is just a representation, no, of the proper biasing ng common emitter. At posibleng magkaroon din tayo ng resistor dito sa ating emitter bago siya ma-connect sa ground. So this is just a representation. As we go on with our discussions, magkakaroon tayo ng mga different examples to illustrate the different components ng ating common emitter configuration and also with the other configurations. Alright? You have here external power supplies or power sources. Kung mapapansin natin, double subscript notation and parehong letter. So we have V sub BB yan. We have V sub BB. Ibig sabihin yan, it's an external power supply na konektado sa ating base and then yung negative ay connected sa ating ground. For this one, we have VCC or V sub CC. Ibig sabihin yan, this is an external power supply that is connected to the collector, and then yung negative ay konektado sa ating ground. Let us check if it is properly biased. Di ba alam natin na ang common biasing or normal biasing ng mga transistors ay base emitter should be forward biased and then base collector should be reverse biased. Tignan muna natin itong base emitter junction natin if it is properly biased. Ang base natin is P-type, ang ating emitter ay N-type. Tignan natin kung tama yung polarity na ina-apply sa kanila. Kailangan forward bias daw. So, positive to P-type and negative to N-type. Forward bias. So, the base to emitter junction is properly biased. But how about the base to collector junction? So, our base is P-type and then the collector is N-type. Kailangan daw yung N-type natin is positive with respect to the base. Alright? Tignan natin dito. This is your external power supply. Positive to N-type. And then tignan natin yung negative kung saan naka-orient. No? Negative to P-type. Therefore, the base collector junction is reversed biased. Okay, so it is properly biased. This is the schematic symbol of our BJT na NPN acting or being a common emitter circuit. Ganun pa rin naman yung kuryente na nag-e-exist sa ating transistor. We have I sub E, I sub B, and I sub C. Since this is an NPN BJT, as you noticed, ang ating arrow dito sa ating emitter ay palabas. Okay. Tignan natin, no? Palabas yung arrow. What is the direction of your I sub E? Palabas din. So, kung anong direction ng arrow na to, kung saan siya nakaturo, palabas or paloob, kung PNP siya, yun din ang direction ng I sub E. Since palabas ang arrow natin, palabas yung direction ng I sub E. And then, opposite lang yung direction ng dalawa. Kung palabas ang I sub E, papasok ang I sub B at ang I sub C natin. Alright? So, that is how we properly bias the common emitter configuration. Alright, so this is the characteristic curve of our common emitter configuration. We have the collector characteristics which represent our output, and we have the base characteristics which represent our input. Now let us zoom into the input characteristics, which is your base characteristics. So let us now take a look at the input characteristics dito sa ating base characteristics. Ang y-axis natin ay I sub B or the base current. Ang I sub B, since ito ay maliit na quantity, no, maliit na kuryente, ina-express natin usually in terms of microamperes. Kasi nga, di ba, ang base layer, ito yung least dope, therefore it has the lowest amount of current. So, microamperes ang ating I sub B. Bakit I sub B ang y-axis natin for the common emitter? Dahil ang I sub B or the base current is the input current of the common emitter configuration. Sa x-axis naman natin, we have V sub BE. Again, double subscript notation. No? So, this is base emitter voltage. Alright? So, this is measured with respect to the emitter. Alright? Bakit VBE ang ating x-axis? Dahil ang VBE natin ay ang input voltage ng common emitter. Okay. So, mag-focus muna tayo dito sa curve na nasa gitna. Yung VCE is equal to 10 volts. What will happen to your I sub B habang ini-increasean natin yung V sub BE natin? Okay. This graph represents yung relationship between I sub B and V sub BE. So, habang nag-i-increase yung VBE, anong nanonotice natin dito sa ating I sub B? From this point, from 0 papunta sa about this point, almost, naman tayo, 0 yung ating kuryente. But when it reaches the threshold voltage, it slowly increases. Alright? Until it fully conducts in the forward direction. So, in this case, kapag na-reach down niya yung around 0.7, of course if it is silicon, ang output voltage daw natin ay 10 volts. Pero what if ang ating input voltage is medyo mas mataas sa 0.7 ng onte? So let's say this is 0.7. Okay? What if medyo lumagpas ng onte yung threshold voltage natin sa 0.7? Probably nasa 0.75 or 0.76 volt. So habang nag-i-increase yung ating VBE, ay slowly nag-i-increase din yung ating I sub B until ma-reach na yung threshold voltage na mas mataas sa 0.7, ang ating output voltage ay mas mataas ngayon. No? So ibig sabihin kapag mataas daw yung ating input voltage VBE, mas mataas yung level ng ating output voltage VCE. But what if mas mababa yung input voltage natin? So ganun din naman, no? So habang ini-increasean natin yung level ng VBE, unti-unti nag-i-increase yung level ng I sub B until it reaches the threshold voltage na mas mababa sa 0.7. Anong nangyayari sa output voltage natin? Mas mababa siya ngayon. Therefore, we can conclude na sa common emitter configuration, kapag ang VBE natin ay mababa, ang VCE natin ay mababa rin. Kapag ang VBE naman natin ay mataas, ang VCE natin ngayon ay mataas. Punta naman tayo dito sa output characteristics natin, no, or the collector characteristics. Ang y-axis natin ay I sub C, which is expressed in terms of milliamperes. While yung kanina, do sa I sub B natin, no, is expressed in terms of microamperes. Therefore, ang I sub C ay mas mataas compared sa ating I sub B. Kaya ang kanyang unit na ginagamit ay naka-milliamperes. Bakit I sub C ang y-axis natin dito sa ating output characteristics? Dahil ang I sub C natin is the output current ng common emitter configuration. Dito sa x-axis natin, meron tayong V sub CE, which is the output voltage. So we have the output current and the output voltage. As you noticed here, meron din tayong different regions of operation kagaya na lang ng diniscuss natin dati sa common base. We have the saturation region and we have the cutoff region. Itong dalawang region na to, may combination ng voltahe at kuryente yan, na kung saan kapag ganun ang combination ng voltahe at kuryente sa transistor mo, ang transistor mo ay ginagamit bilang isang switch. Dito tayo concerned. Dito sa white part na to, no? So this is your linear amplification region, or also known as the active region. As you notice, compared with the graph of your common base dito sa ating common emitter, hindi horizontal yung graph natin. Unlike dun sa common collector, di ba, straight na straight yan. Kapag na-reach na yung saturation, straight na yan. Okay? Pero dito sa ating common emitter, hindi. Medyo may onting curve pa siya, and then nag-i-increase ng paunti-unti pa. Itong mga levels na to, kung mapapansin natin, naka-microamperes. So bakit siya naka-microamperes? Because these are different levels of I sub B. Okay? For the corresponding levels ng ating I sub C. Alright. For example, in-increasean natin yung ating VCE. What will happen to I sub C? I sub C will slowly increase until it will saturate. Ibig sabihin ng saturation, ito na yung pinakamataas na pwede niyang increase. So in this case, for example, nandito tayo sa 2 milliamperes para sa ating I sub C. What is the corresponding I sub B? So ipoproject natin dito, the corresponding I sub B is 20 microamperes. So halimbawa daw, no, kapag meron tayong 20 microamperes na input current I sub B, ay meron tayong corresponding 2 milliamperes na output current I sub C. Remember sa ating common base, meron tayong tinatawag na alpha or the amplification factor or yung current gain ng common base configuration. Diba kapag sinabi nating gain, that's an output quantity divided by an input quantity. Now, if it is a current gain, output current divided by the input current. Ang beta is actually a current gain din. Pero this is a current gain or amplification factor ng isang common emitter amplifier or common emitter configuration. Ano kaya yung equation natin for beta? Remember, ang output current natin sa common emitter is I sub C. Ang input current natin sa common emitter ay I sub B. So, kung i-divide natin yung output divided by the input, makukuha natin yung gain. So, we have IC, which is the output current, divided by I sub B, which is the input current. No? Gain yan. No? But it is more appropriately expressed as beta DC. Or kahit alisin na natin yung subscript na DC na yun, no? Ang ibig sabihin nito is beta or the amplification factor ng common emitter configuration. So, in AC mode kasi, kapag meron na tayong input na AC signal, no, magkakaroon tayo ng variation, no, sa ating load line or dun sa ating characteristic curve. Okay? Beta AC is equal to the change in IC or delta IC divided by change in delta IB. So it's basically the derivative of IC with respect to the derivative of IB. Ang beta AC is also referred to as HFE, which is a hybrid parameter. Don't worry about this term for now kasi pag-aaralan natin to pagdating na natin sa AC analysis sa hybrid model natin. Alright? In transistor specification sheets or data sheets, ang beta is expressed as HFE. So kapag nakita natin HFE doon sa ating data sheet for specific transistor models, beta rin yan. How do we solve or how do we determine the level of beta AC graphically? For example, meron na tayong characteristic curve kagaya nung kanina, no? So let's just zoom in dun sa ating characteristic curve. Alright. What if the signal varies, no? And ito yung kanyang natatamaan na points. We have IB1 and we have IB2. So nagva-vary daw sa pagitan ng IB1 at IB2, no? Yung ating signal. And of course, kapag may variation tayo sa IB, may variation din tayo sa IC. So ang variation sa IB, that is delta IB. Ang variation sa IC is delta IC. So kukunin lang natin or isa-substitute natin dito sa ating equation, no? Hindi ba't ang beta AC ay change in IC with respect to change in IB? Here is your change in IC. So tignan natin dito sa ating graph, no? Between these 2 points, kung i-project natin to pakaliwa, no, meron tayong corresponding levels of IC. We have IC1 and IC2. So, ima-minus lang natin yon. This is 3.2. Ito naman, this is 2.2. So, nilagay natin dito, 3.2 milliamperes minus 2.2 milliamperes. So, that is the change in your I sub C. Kung ima-minus natin to, no, 3.2 minus 2.2, that is equal to 1. So, ang sukat daw ng ating delta IC dito, this is 1 milliampere. Alright. May corresponding change din tayo dun sa ating I sub B. So, we have IB1 and IB2. Yung IB1 is 20 micro. Yung IB2 is 30 micro. Kaya ima-minus lang natin yon. 30 microamperes minus 20 microamperes is equal to 10 microamperes. So, yun yung pagbabago sa I sub B natin. And then, balik tayo dito, no, sa ating equation. 1 milliampere divided by 10 microamperes at VCE equals 7.5 volts. Ito, no, this is 7.5 volts. This is your Q point. This is the actual voltage ng ating collector and emitter terminals. 1 milliampere divided by 10 microamperes is equal to 100. Yun yung current gain natin for AC. Ang DC beta naman natin is calculated using DC values. So magre-refer tayo ngayon dun sa ating Q point. Ang ating Q point is narito, ipoproject natin pababa, we have 7.5 volts. That is your DC collector to emitter voltage. Ipoproject natin ngayon pakaliwa dito, no? Magkakaroon tayo ngayon ng corresponding IC. Ang IC natin at that point is 2.7 milliamperes. So this is 2.7 milliamperes. No? For the corresponding level of 2.7 milliamperes, ano daw yung corresponding I sub B niya? We have 25 microamperes. So this is IC. Ito yon, nung pinoject natin pakaliwa yung Q point. Ano daw yung corresponding IB niya? 25 microamperes. So we have 108 as our DC beta. This is still the current gain. No? Kung mapapansin natin, halos pareho din naman ng value yung AC beta tsaka yung ating DC beta. We need to determine the relationship between alpha and beta. No? Alam natin na itong alpha, this is the current gain ng isang common base. Or that is the amplification factor ng isang common base. While ang beta naman, this is the current gain or amplification factor ng isang common emitter. How do we relate the two quantities? So we have the basic relationship between or among the three currents. Now we have I sub E equals I sub B plus I sub C. As you noticed, capital po yung ating mga subscript dito kasi ang pinag-aaralan muna natin dito are all DC quantities. Alright? Next, we know that the equation for alpha is equal to output current IC divided by input current IE. And beta is equal to output current IC divided by input current IB. Next step is to replace everything, every term dito sa ating equation for the currents. No? Express natin to in terms of IC. Kinakailangan ang kuryenteng matitira lang dito sa equation na to ay in terms of IC lang. So unahin natin tong I sub E. Diba we can relate IE and IC by alpha. If we're going to rearrange this equation, pwede nating palitan yung IE ng IC over alpha. How about this one, IB? Alam natin ang relationship between IB and IC ay beta. So we can replace IB here by IC over beta. Kung mapapansin natin, itong equation na to, pareho din lang man sa equation na to, pero ang kuryente natin are all in terms of IC. We can cancel out the ICs here. No? Ang matitira is 1 over alpha equals 1 over beta plus 1. Alright. This is an assignment for you. I want you to solve for alpha and I want you to solve for beta. So you will have two equations. Alright. Alpha equals this one and beta equals this one. Now we're going to determine the relationship between the emitter current and the base current. Kasi normally kapag nagko-compute na tayo ng mga different parameters, DC parameters, for the different circuit configurations, ay inire-relate natin ang IE tsaka yung IB. So ngayon pa lang, i-establish na natin yung relationship between the two. So magsisimula tayo doon sa basic equation ng kuryente. IE is equal to IB plus IC. We know that beta is equal to output current IC divided by input current IB. So papalitan natin ngayon yung IC in terms of IB. Kasi nga gusto natin i-relate ang IE tsaka ang IB. So dapat ang matitira sa equation na to ay IE tsaka IB terms lang. Walang IC. Okay. So we can replace IC by beta times IB. So pareho lang yan. Iba lang yung terms. Okay? And then, factoring out IB, magkakaroon tayo ngayon ng IE equals beta plus 1 times IB. So, this is the relationship between the two currents. Magagamit natin ito pagdating natin sa mga examples natin, calculating for the different DC parameters. We now go to the common collector configuration. Ito yung pangatlong configuration ng bipolar junction transistor. Kung mapapansin natin, itong ating common collector configuration, ang ating collector terminal ay nakakonekta direkta sa ating ground. No? For PNP and NPN, no? Ang collector, rekta sa ground, rekta sa ground. Ang emitter naman natin ay nasa taas. Unlike sa common emitter kanina, collector yung nasa taas, emitter yung nasa baba. Ang input terminal natin for the common collector is yung base. So, the input side is composed of base collector, while the output side is composed of emitter collector. So, these are your external power supplies. Tignan natin if they are properly biased. So, dito muna tayo sa base emitter junction. No? We have P-type for the emitter and we have N-type for the base. Kinakailangan daw naka-forward bias siya. Meron tayong positive bias dito sa ating P-type and then we have a negative bias naman dito sa ating N-type. Ang positive bias is provided by VEE and ang negative bias natin is provided by VBB. Therefore, properly bias ang base emitter junction natin. Naka-forward bias sila. Ito namang base collector junction natin, no, dito manggagaling yan sa VEE. We have positive to N-type and then negative to P-type. Therefore, naka-reverse bias ang base collector junction natin. It is properly biased. And these are the schematic symbols. Ito yung para sa PNP. Ito yung para sa NPN naman natin. So kahit na common collector configuration siya, yung kuryente ay ganun pa rin. No? For example, dito sa ating PNP, ang arrow ay papasok. Therefore, susundan ng IE yun. So papasok yung IE. Kapag papasok ang IE natin, palabas yung IB at IC. Kabaliktaran naman sa NPN. No? Palabas yung arrow natin, therefore palabas yung IE natin. Kapag palabas yung IE, papasok naman yung IB at IC. This is the common collector characteristic curve. Actually, similar lang yung characteristic curve ng common emitter tsaka ng common collector. No? But the main difference is yung ating output side. Sa ating output side, remember sa ating common emitter, no, ang y-axis ay I sub C because the output current is I sub C. Sa common collector, ang output current natin ay I sub E. Therefore, kung ito ay para sa common collector, kailangan palitan natin ito ng I sub E. And then, the rest is just the same. Ang common collector is normally ginagamit natin hindi bilang isang amplifier, no? Hindi rin bilang isang switch. Although, pwede rin natin i-configure in such manner, no? Pero kukuha tayo sa collector as an output. Dito kasi sa common collector, kumukuha tayo ng output sa emitter. That's why it's also called an emitter follower. Ang common collector ay ginagamit natin as an impedance matching circuit. No, halimbawa, meron tayong load na mababa ang impedance. Isang example nito is yung mga speaker natin. No? Normally, mga speaker nasa 4 ohms, 8 ohms, mababa yung impedance. Kapag kinabit natin siya direkta sa isang amplifier ng walang impedance matching device, magkakaroon tayo ng tinatawag na loading effect. Yung loading effect, ito yung pagbaba ng signal or ng voltage natin dahil mababa ang ating load. Okay? So, halimbawa, ang output natin is supposed to be, let's say, 10 volts. Pero dahil mababa yung ating load, no, bababa na lang ito sa ating output voltage. So, kinakailangan natin ng device sa pagitan ng amplifier at ng mababang impedance na load. No? Ito yung tinatawag na impedance matching circuit. Ang common collector ay merong mataas na input impedance at meron siyang mababang output impedance. Kaya pasok na pasok siya, no, as an impedance matching device. So halimbawa yung amplifier natin is high impedance, no, at ang load naman natin ay low impedance, kinakailangan mo ng device na mamagitan doon sa high impedance source and low impedance load. And that is your impedance matching circuit, which is your common collector. How do we solve for the power dissipation ng ating mga different configuration? When we say power dissipation, ito yung we can simply say that ito yung kinakain na power ng ating transistor, no, based on the different configuration. So ang una, we have the common base. Ang equation natin dyan ay PC max or the maximum power dissipation equals VCB times IC. Bakit kaya VCB times IC yung ginamit natin? Kasi ang VCB sa common base is output voltage, while I sub C is output current. So basically, ang ating maximum power dissipation, ang ginagamit natin dyan ay ang output parameters natin. Sa common emitter naman, we have VCE times IC. Dahil ang VCE ay output voltage at IC naman ay ang output current. Sa common collector, we have VCE pa rin ang ating output voltage. Dahil sabi ko sa inyo, di ba, similar din ang common collector sa common emitter. But ang pinagkaiba nila, ang output current is I sub E. Kailangan matutunan din nating magbasa, no, ng specification sheet or ng data sheet na tinatawag. Kasi nandirito yung mga different values, different characteristics ng mga transistors or any electronic device na gagamitin natin para sa ating circuit. Ito yung mga basic transistor parameters sa ating data sheet or specification sheet, no? I-zoom in lang natin. Normally, makakakita tayo ng tinatawag na absolute maximum ratings sa mga data sheet. Ibig sabihin yan, ito yung pinakamataas na voltahe, pinakamataas na kuryente, so on and so forth, no, na hindi pwedeng malagpasan. So, nakaset na yan or naka-indicate na yan dun sa ating mga data sheet. For example, collector to emitter voltage of your transistor is 30 volts DC. No, by the way, itong transistor sa example natin is an NPN. This is 2N4123. Alright? So, this is a TO92 packaging. Ito yung pin configuration, no? Yung emitter, base, and collector. So, hindi lahat ng transistor models pare-pareho ng pin configuration. So, you still have to check the data sheet for the proper pin configuration. So, ito yung TO92 or yung plastic package. So, balik tayo dito. The maximum collector current daw is 200 mA. So, ibig sabihin, ito yung pinakamataas na collector current na kayang i-handle ng ating transistor. Total device dissipation, we have 625 milliwatts. So, basically, this means na hanggang 625 milliwatts ang kayang power na i-handle nitong ating transistor. Ano kaya itong derate above 25 degrees Celsius na to? This is what we call the power derating factor. Habang umiinit yung ating device, no, nagkakaroon tayo ng bawas sa maximum power. Ang maximum power natin in this case is 625 milliwatts at 25 degrees Celsius. But what if tumaas yung temperature natin, naging 26 degrees Celsius? Dito tayo magbabase ngayon. What will be the new maximum power? So, dito tayo sa power derating factor. This is 5 milliwatts. Actually, this is per degree Celsius. Alright? So, ano na yung magiging maximum power natin kapag 26 degrees Celsius na siya? Magbabawas daw tayo dito. So, magiging 620 milliwatts na lang. No? So, nakikita natin dito na nagkakaroon pala ng effect yung temperature natin sa maximum power. Habang tumataas yung temperature natin, no, the lower the maximum power is. So, yun yung tinatawag na power derating factor. Next, we have the collector emitter breakdown voltage. So, it's a minimum of 30 volts DC. So, kung mapapansin natin dito, IC is equal to 1 milliampere DC and IE is equal to 0. So, this is the off characteristic. No? So, ibig sabihin, ito yung VCE natin, no, kapag naka-off yung ating transistor. Ang minimum daw ay 30 volts. The collector cutoff current, no, ito yung IC natin. No? Alam natin na kapag naka-off yung transistor, ibig sabihin, dapat walang kuryenteng dumadaloy. Pero in reality, merong maliit na kuryente na dumadaloy. No? That is the collector cutoff current or also known as ICBO. Alright? Ang maximum value daw nito ay 50 nanoampere. So maliit lang to, no? Kaya we can approximate this to be 0. Okay? Kapag cut off, 0 ang kuryente approximately, ang voltahe naman natin ay mataas. And also it will depend on your power supply. In our future lectures, magkakaroon tayo ng mga examples, no, to calculate the saturation levels and the cutoff levels ng mga transistor natin. Next, we have the on characteristics. So, meron tayong gain. Remember yung beta, no? That is IC over IB, or the output current IC divided by the input current IB. It's also known as HFE, which is a hybrid parameter. No? I-discuss natin to pagdating natin sa AC analysis. So, kung mapapansin natin, ang unit nito ay wala kasi unitless siya. Gain ito eh. Okay? So, ang minimum natin ay 50, ang maximum ay 150 for this particular type of BJT. Okay? And for different levels of IC and VCE. So, basically, ito yung beta natin, yung HFE. Okay? Next, collector emitter saturation voltage, VCE SAT. Remember, kapag nagsasaturate yung ating transistor, no, ito na yung pinakamataas na kuryente, pero ito yung pinakamababang voltahe. Theoretically, VCE is 0 if nakasaturate or naka-on ang ating transistor. Tignan natin actual value. So this is 0.3. So hindi naman talaga eksaktong 0. Meron siyang maliit na voltaheng nag-i-exist sa collector to emitter kapag ito ay nakasaturate. But anyway, para mas maintindihan natin, magkakaroon tayo ng future discussions and examples para dito sa transistor circuits natin. Small signal current gain, HFE, 50 to 200. So this is still your beta. No? How do we test transistors? Meron tayong method, no, para matest yung mga transistors natin kung gumagana ba siya. Ako normally I use a multimeter na merong transistor checking function. Meron siyang emitter, base, and collector na butas, and then pipihitin lang natin sa HFE, itutusok natin yung transistor dun sa mga butas na yon. So anyway, if we have the chance to conduct a laboratory, no, dito sa semester na to, hopefully, because of what's happening around us, no, ituturo ko sa inyo yung actual na pag-test ng transistor using the transistor checking function ng isang digital or analog multimeter. But basically, we have three ways, no? Curve tracer, ito yung medyo complicated na way para matest yung transistor natin. Diba, we have the input and we have the output characteristic curves. Yung curves na yon, palalabasin mo dito sa device na to, yung curve tracer. Ito medyo may kamahalan ito. But ito may ensure natin na matetest natin properly yung transistor natin kung tama yung voltage saka yung currents na dadaloy sa kanya for a specific range. Alright? Yung DMM naman, digital multimeter, no, ito yung sinasabi ko kanina, no, meron siyang transistor checking function. So magpa-flash ako mamaya ng picture ng DMM, or kahit yung analog meron ding transistor checking function, no? Pwede rin tayong gumamit ng ohmmeter. Okay? So for the ohmmeter kasi, ako personally, kapag ohmmeter function yung pantest natin, I prefer the analog one. No? I think tinuro naman sa inyo kung paano mag-test ng diode using an analog multimeter. Ganun din yung way kung paano natin ite-test yung BJT natin, no, using an analog multimeter. Remember kasi ang BJT, parang dalawang diode yan na naka-back to back. Diba? Meron tayong emitter diode and meron tayong collector diode. So, kung paano natin tinetest yung diodes natin, ganun din natin ite-test yung transistor natin. Kung gagamit tayo ng analog multimeter na nakaset sa ohmmeter range natin. So these are the different transistor packaging. No? So anyway, ma-encounter nyo to, no, kapag nagde-design na kayo ng mga actual circuits and kapag nag-perform tayo ng uh, experiments natin. Alright? Uh, I hope you understood no, yung topic natin for today, yung common emitter tsaka yung common collector natin. If you have any questions dito sa ating lecture, please post it on our group chat. So that would be all, and thank you.